They're from Arizona originally.
But then I can come back.
Begin class. I'm late. Okay, well, we're not going to begin class yet because it can't even recognize my thumb drive yet. Well, we should give bonus points for showing up on such a beautiful day, don't you think? Okay. Yeah, that's maybe good, considering. Jeff, it's not reading my thumb drive. That's kind of a problem. Okay, let's try a different thumb drive. Let's try a different port. Oh, now it's going to work. I just put it in this front one, and it didn't listen to me. And now it might be listening this time. No, it's still not. Oh, there it is. It's fine now. Maybe it's just me. Maybe it's just me. I may have been looking. It's sunny day fever.
Yeah, that's it.
Okay, I've already lost where I am. Keep putting on the wrong thing. Here we go. 9, 40, 41. Okay, now it won't open up the file.
What days are exam?
Wednesday, 3 to 4, 3 to 5.
Wednesday, that was it. Second.
There we go.
You just that trick now.
Yep, I had to use that trick how many times in this class? All right, sorry for the delay. We're ready now. Okay, we're on the last subject of the course, which is rheometry. And rheometry is measuring rheological properties. So we finished with our modeling. We did our complex constitutive equations. And now we're going to go back to a necessary topic, which is how do we get this data that we've been pointing to and trying to model all these weeks? And the answer is we go and use a rheometer. And I do teach a class in the fall on taking measurements on rheological instruments. And we use this same chapter, chapter 10, and we actually put our hands on the instruments and get the data and do some analysis. So the homework that we have for next week is doing some of this analysis yourself. And it's very simple to do in terms of either just showing up in front of certain instruments. Certain instruments are very easy to handle. Learning how to load the samples, learning how to push the buttons. The instrument does a lot of calculations for you, and then you get answers. The details behind where some of those formulas come from is what we're going to talk about this week, today and next week. In particular, I'm going to go through some of the calculations for the capillary rheometer, which are the most complicated to derive, although very easy to use. So as with a lot of engineering practice, you can just grab the formulas and plug the stuff in and get answers. But if you want to know what goes into it and what it's being assumed, then you need to follow these derivations a little bit. I don't have time to derive everything, but we're going to concentrate on the capillary data. And you're going to see that there's kind of a pattern. And then if you want, you can go through the book. There's descriptions of the parallel plate, the Conan plate, and the Couette flow. And then, in fact, newer geometries that you might encounter or that you might, in fact, invent yourself. So we're going to talk about mostly shear flow, although I am going to talk a little bit about elongational flow as well. So in general, we've been talking about rheology. Ology means study of. Metry means measure of. So this is measurement of flow, rheometry. We introduced many, many weeks ago that we have two standard flows, shear and elongation. And so we're going to need to take measurements in both shear and elongation. So in shear flow, going way back to the beginning, shear flow is a flow that has relative motion between the layers. And what we want to do is produce these flows. We've been always saying that if we have shear flow, we must impose on our samples this sigma dot x200, which we know in the 1, 2, 3 coordinate system is a shear flow that looks like this. If we move this top plate with a velocity v and the bottom plate is stationary, we get a linear velocity profile, which is given by v. And if it's a steady flow, if we move a constant v over the gap h, that's equal to gamma dot naught. And it's a very simple situation. The problem is that it's not that easy mechanically to take a very viscous material, put it between two plates, and move the top plate and figure out what that force is. It's very hard to keep those plates separated at exactly that constant gap. And as you shear it forward, let's say you started out with a sample that was the shape of the book here, and then you move the top plate, eventually you would get a distorted sample that wouldn't be anything like our imaginary system. So if we started off with a sample that was this shape, and we're shearing it, eventually it's going to be this rhombus shape, and eventually it's going to be ridiculous. You have some ridiculous shape like this that's no way really reflecting this total flow that we were trying to produce in the first place. So this parallel plate flow, it's difficult to produce perfectly, and it has this problem of very difficult to have a steady flow. There's always these sort of edge-related effects. And it's not the most common way of measuring shear properties. The most common ways are the ones I'm going to discuss in the next couple of lectures. So the general shear flow case is shown here. This instrument does exist, but it's not very common. You can try to balance out the forces by putting two samples in between double parallel plates, and this is a little bit more stable. There were commercial instruments based on that geometry for some period of time, but not so common anymore. The most common are these two, parallel plate, Conan plate, couette flow. This one, the double couette, is sometimes seen. And then the one I'm going to talk about first, which is the capillary rheometer. So the capillary rheometer is flow through a tube. So we studied numerous times flow through a tube. We usually drew it as a tube like this, and we said, oh, there's some velocity profile in the tube. We said it was long, and then we didn't have to worry about the edge effects. But if we're actually going to produce this flow, we need to somehow feed fluid into it. It may be long, but it's not infinite in length. So we need to feed fluid in. So usually we put a big reservoir above the tube, and we feed material through by forcing a piston. So this is maybe a piston that's moving downward. There's polymer or a composite or peanut butter in this reservoir. It enters the tube through a contraction. It goes through this long tube, and then it exits. So it's a very practical idea to do this capillary flow, but it introduces changes to our analysis from what we started off with. We said don't worry about the ends, and now we definitely have some interesting things happening at the ends. There are entry effects. There are exit effects. And we're going to talk about how to take those into account. There's also, during our analysis, we assumed no slip at the wall. And that's mostly true, but there are times that that's not true as well. And I'll talk a little bit about that. And maybe the big picture, the first thing I should really talk about is why flow in a tube would be a good analysis for shear flow, when in fact it's not shear flow, it's this parabolic velocity profile in a tube. So addressing that issue first, if I go back a couple of slides, this is what's happening inside the capillary tube itself. There are layers of fluid telescoping one inside the other. So if we go back and look at our solution to capillary flow, flow in a tube, we know we have some, for a Newtonian fluid, we have a parabolic velocity profile. For a power law fluid, it's a little flatter. And when we look at this velocity profile, we see that near the wall, it kind of does look like shear flow. And it is shear flow, right here near the wall. So there is a very nicely defined shear flow near the wall. And that's what we're going to use in our calculation.
But then when you model it, then you'll have to like take into account the pressure drop too.
Yes. The pressure drop and the flow rate are the two main variables that are measured for this flow. So let's look up close near the wall in the capillary tube. We normally analyze flow in a tube in the cylindrical coordinate system, Z and R. If we zoom in near the wall, we've got this shear flow. We want to relate that to a viscosity measurement. So what we'll do is we'll define a coordinate system near the wall, a shear coordinate system. The flow is in the one direction, which is clearly Z. The gradient is in the two direction in shear flow. Okay? The gradient in our flow is in the two direction, which compared to the R direction is minus R. And the three direction is the neutral direction, which is perpendicular to 1 and 2, and so that would be negative E theta. It's negative because you take R cross Z and you get minus theta to get a right-handed coordinate system. All right, with that translation, we can then figure out what tau 21 is, which is the one that appears in the definition of viscosity down here. Tau 21, 2 is minus R, and 1 is Z, so it's minus tau RZ evaluated at the wall. And we're going to define that as minus tau R. The shear rate, this gradient near the wall, is dV1 dx2. So dV1, which is Z, dx2, which is minus dER. And so the shear rate at the wall, which is in this flow minus dVz dr, is just equal to, is defined as gamma dot R. So when we take the ratio of minus tau 21 divided by gamma dot naught, which is our usual way of calculating viscosity in shear flow, we get minus tau R times minus 1 divided by gamma R. So if we can figure out in capillary flow what the shear stress at the wall is in its natural coordinate system, and what its shear rate at the wall is in its natural coordinate system, we can take the ratio and we'll get the viscosity. Now, one thing to note about that is that this is going to evaluate the properties of the fluid near the wall. So let's say you put peanut butter in there, and if peanut butter is reasonably homogeneous, and if the properties near the wall are the same as the properties everywhere, it's going to give a good value of viscosity. If you put peanut butter mixed with rice, okay, just dry rice, uncooked rice, side of a filler particle, you know that near the wall, okay, this would have to be a pretty big capillary to fit the rice in there, so you have to imagine that. If we put something that had a particle in it, a bunch of rice, let's say, near the wall, the rice can't go through the wall, right? And so there's actually a phenomena called a depletion layer near the wall. So because this rice, maybe a particle would like to be like that, and it can't be, the particle simply can't get to that position, you end up with a little depletion layer near the wall. And so all of our formulas are messed up, because all of our formulas are based on what is the shear flow like near the wall, and if there are wall effects, it's going to mess up our calculation. So that's something always to keep in the back of your mind when you're dealing with inhomogeneous material. It has fewer. It has fewer. So if you imagine marbles or something bouncing around, they propagate all throughout the space, but when they get near the wall, they can't propagate through the wall. So they're pushed away. They stay away from the wall, exactly. All right, so all we've done so far is look up close at the wall, and we've seen that we need to go back to our solutions for in the microscopic balances to figure out what tau r is and what gamma dot r is. Now, what we can't do is use a constitutive equation. We can't say, well, let's assume it's a Newtonian fluid and solve the problem. Because the point of this instrument is to measure rheological properties. And we don't know that it's a Newtonian fluid. It's catch-22. If we assume it's Newtonian and then get a number, we can't really tell what that number is because we've already assumed Newtonian. If we assume power law fluid and then get a number, the number is also suspect. So we need to make a calculation of a wall shear stress and a wall shear rate that has no constitutive assumptions in it at all. That's the tricky part about rheometry. So let's do the easy one first, the shear stress at the wall. All right? And we're going to solve the momentum balance, the massive momentum balance. And the momentum balance. But we're not going to assume a constitutive equation. But that's okay because we're looking for stress. So stress appears in the momentum balance. The mass balance for a incompressible fluid is del dot V equals 0. And we know that the velocity is only in the one direction, or the z direction, let's say. And we've done this many times. We get dvz dz equals 0. The momentum balance, rho dv dt plus v dot del v equals minus grad p minus del dot tau plus rho g. We're going to do steady flow. It's unidirectional. And we could neglect gravity, but you can also wrap the gravity up into the pressure using this little technique that's shown on my slide here. If I write that a new pressure, a capital pressure, is equal to the pressure minus rho gz, then grad capital pressure is equal to grad little pressure minus rho g. And that's what this term turns into for the flow that we have. So we can just write this as this modified pressure and get the final momentum balance. Now this equation I have written on the slide here in cylindrical coordinates. And I've simplified the tau term by assuming no theta dependence, so all the theta derivatives went away. I did assume a long tube, so I took out the r dependence. And I assumed that the stress tensor was symmetric. So there are a few terms missing, but they're all in these assumptions here. And only with those assumptions and concentrating on the z component, we can get an equation we can solve. So the z component of the equation of motion is dp dz equals 1 over r d by dr of r tau rz. So if I separate these into a function of z only and a function of r only, we've done this many times. We can solve that pressure part. We've done that many times. I can just write the answer down. P minus P over L z plus P naught, like that. Telling us that lambda is PL minus P naught over L. If I define delta P as P naught upstream pressure minus downstream pressure, then lambda is minus delta P over L. Okay, now we plug that back in up here. Minus delta P over L equals, I'm pulling this equation down, 1 over r d by dr of r tau rz. We're looking for the shear stress at the wall, and this is an equation we can solve. This is the easiest calculation we're going to do here. So I'll multiply through by r. And then integrate once with respect to r, and I get minus delta P over L, r squared over 2 plus a constant equals r tau rz. What's inside the parentheses? Integrate the left side, I just get r squared over 2 plus a constant. Integrate the right side, I just get what's in the parentheses. Divide by r, and I get minus delta P over 2L times r plus C1 over r is equal to tau rz. For boundary conditions, can you suggest a boundary condition that might work in this case? What happens near the center of the tube? R is 0. Stress.
Flow is max.
Yeah.
Stress, not just maximum. When R is 0, what does this term go to? Infinity. So is that reasonable? In fact, near the center, in the center of the tube, okay, the stress is high in the walls, but it actually is at its lowest stress. The gradient here, remember, for our fluids, dV, dr is proportional to stress for most of our fluids. And here, dV, dr is 0. So the stress is actually small in the center. So if we just say that the stress is finite at r equals 0, then that must mean C1 is 0. So we get tau rz is equal to minus delta P over 2L r. It looks like I dropped a minus sign. I apologize for that. Yeah, but I don't want to. Here's the missing minus sign. You see it right here? I missed it right here. So that means it's here, which means this isn't here. I missed the minus sign in front of the grad tau. So the shear stress in a capillary tube is delta PR over 2L. And at the wall, which is the one we were interested in, tau R, it's delta P capital R over 2L. So that was easy. If we go back, we have half of what we needed. We now need the shear rate at the wall. This is a little bit more difficult. Okay? The shear rate of the wall comes from this expression for the velocity. If we knew the velocity, everything would be fine. So for instance, we know the velocity for a Newtonian fluid. Okay, so let's just for practice calculate that. We need gamma dot R, which is minus dVz dr evaluated at R equals R. So I'll just say, but we don't know Vz of R. So that's our problem. And we will never know it. I mean, these are meant to be measurements on unknown fluids. If we knew the velocity field, we'd be done. Okay? We want to just stick a polymer into this instrument and make it go. So there is a technique, and I'm just going to lead up to it by first practicing on a Newtonian fluid. So let's try the Newtonian calculation. Okay, for the Newtonian calculation, over here I have the velocity field. We've solved for that before. We have Vz of R is equal to 2 times the flow rate over pi r squared times 1 minus r over r quantity squared. So we can take this derivative, dVz dr equals all the stuff out front times minus 1 times 2 r over r times 1 over r. All the stuff out front, this minus sign, and then 2 times the quantity itself times the derivative of that quantity with respect to r. So I get minus 4q over pi r to the 4th times r. We are interested in gamma dot r, which is minus dVz dr evaluated at the wall. So that's minus 4q over pi r to the 4th, where r is equal to evaluated at the wall. So I get 4q over pi r cubed. So to calculate for a Newtonian fluid, the viscosity equals tau r over gamma dot r, it's equal to delta PR over 2L divided by 4q over pi r cubed, and you're done. Or you can be a little more statistical, and you can plot 4q over pi r cubed versus delta PR over 2L and get a line and do a linear regression. And the slope is 1 over the viscosity. Or you can plot them the other way. This is the way we usually plot them. That's not really my choice. And then the slope would be viscosity if you put stress up here and rate down there. But nevertheless, this is a way of averaging the results. And you could check also that the results you're getting are really going to go through 0 as they should, and that you can actually look at the scatter of your data if you plot it this way. This quantity, 4q over pi r cubed, is defined as gamma dot apparent, okay? Apparent shear rate when it's not a Newtonian fluid. Okay, so 4q over pi r cubed is the wall shear rate when it's a Newtonian fluid. When it's not a Newtonian fluid, it's a number that's going to figure in our answer, and so we give it a name. Notice also the independent variables are pressure and flow rate. So that's one you were asking about that. In this flow, the independent things that we measure are the pressure drop across the capillary tube, the flow rate. We need to know the capillary radius and its length, and that's all we need to get viscosity. If we were dealing with the power law model, we could do the same thing. We could take the derivative of the power law solution the same way we did here. It would obviously come out differently. And then take whatever answer we get and put it into this formula. And it comes out like this. If you, do I have it? If we do the same calculation for power law fluid, we get that gamma dot r is equal to 4q over pi r cubed, the Newtonian result, times 1 over the power law index plus 3 over 4. Again, using the solution to the power law model, and the details are in the text, you can find that this quantity, 4q over pi r cubed, etc., from the solution for a power law model, you can solve that this gamma dot r quantity is also equal to the wall shear stress divided by the consistency index raised to the power 1 over n. The relationship between this and this is the relationship between Q and pressure drop. So if we put the result for flow rate versus pressure drop in here and rearrange, we get this quantity. If we rearrange this, we can get a plot, the one I show here. I don't think it's worth going through, but it's possible to make a similar plot of apparent shear rate versus wall shear stress that allow you to calculate the power law parameters. The slope of the line is 1 over n. And the intercept at 1, 1 here can give you the consistency index. The details are just a little bit of calculus, nothing too exciting. The problem is that we really didn't want to have to assume any of these things, and in fact, it's really unacceptable that we would have to assume either Newtonian or power law. What we would like to do is calculate this shear rate at the wall for the general non-Newtonian case. Okay? For the Newtonian case, it's going to be a higher shear rate typically than for a shear thinning fluid. The shear thinning fluid has a flat center, and as a result, it has a steeper wall here. Okay? So it has a higher shear rate at the wall. So there is a correction, and the solution for this correction comes from a consideration of the pressure drop flow rate relationship. How can we express gamma dot R for a general non-Newtonian fluid? This derivation is called the Weisenberg-Rabinowitz correction. And it's very clever. It's nothing I would have come up with myself. So I'm really presenting to you someone else's work, obviously. And it comes down to the expression for flow rate as a function of velocity field. Flow rate is equal to 2 pi times the integral over the velocity over the entire cross-section of the tube. This is our general formula for calculating flow rate from velocity field. We're going to play around with this a little bit using some clever calculus to get it to turn into an expression that will relate shear stress and flow rate. First, we integrate by parts. Okay, so the integration by parts is the integral of u. V is equal to uv minus the integral of v du. For u, I'm going to use the velocity. For dv, I'm going to use r dr. So that means du is equal to dvz dr dr. And u dv, that's the regular dv there. Integrate this, I get r squared over 2. I'll move this tau, the 2 pi over to the left just for a holding pattern there. And now I'll do the integration by parts. The integral of u dv is equal to u v minus the integral of v du. The integral of u dv, integral of u dv is equal to u v minus the integral of v du. We can carry out these limits here. Q over 2 pi equals Vz at the wall, which is 0, minus, times r squared over 2 minus v in the center, which is a big number, times 0. So in fact, this whole thing goes out. So we get minus the integral 0 to r of r squared over 2 dvz dr dr. Now I'm going to call minus dvz dr gamma dot. And I'm going to go back to our result for stress to rewrite R in terms of stress. Tau RZ is equal to delta P R over 2L. So I can say that R is equal to 2L over delta P times tau RZ. And I can say that dr is equal to 2L over delta P d tau. I can change the limits when R is 0, tau is 0. And when R is cap R, the upper limit, tau RZ is delta P cap R over 2L, which is tau R. All right, substituting all those things together. Q. Let me put this 2 over on the other side as well. Q over pi equals the integral from 0 to tau r of r squared, which is 2L over delta P squared tau RZ squared, gamma dot, dr is 2L over delta P d tau RZ. Question?
Oh, never mind.
Got it? I'm going to take all my constants out and move them to the left again. That's my strategy for not making algebra mistakes. So I've got Q over pi. I've got delta P over 2L cubed equals the integral from 0 to tau r, tau RZ, gamma dot, d tau. Now, I'm just going to play around here on the left here for a second. Delta P over 2L is almost delta PR over 2L. Okay? So if I sneak an R cubed over R cubed here, then I've got delta PR over 2L. I have tau R cubed, if I associate this one here. And this one is like 4Q over pi R cubed. Okay, this one is like gamma dot apparent, except I need a 4 over 4. So I've got a 1/4 gamma dot A tau R cubed on the left. So far we've just been playing around with variables, but we did start with the flow rate, which was a very interesting way to start. We've managed to turn it into an expression that has these same 2 variables in it that we've been plotting previously, the apparent shear rate and the wall shear stress. So there is some logic there that's indicative that we're kind of on an interesting track. The next step is totally unintuitive, really, but maybe the brilliance of Weisenberg and Rabinowitz. What they said was, well, let's take the derivative of this expression with respect to tau r, okay, with respect to tau r. And the idea is that it's going to turn some of these terms into, like, actually what term is going to appear is d gamma dot apparent d tau r is going to appear when we take that derivative. And that's what we've been messing with here, right? The derivative of gamma dot apparent with respect to tau r. Or in the one we didn't quite finish, again, some sort of slope of gamma dot apparent with respect to tau r. So maybe there's a way that mere mortals could have thought of doing this, but in any case, it was pretty smart on their part. Okay, so now we'll take the derivative of both sides with respect to tau r. The left-hand side is easy. The right-hand side requires Liebnitz rule. Okay, so the left-hand side is a product rule. So we have 1/4 times the product rule. The first times the derivative of the second plus the second times the derivative of the first. So this is the left-hand side, and that's equal to the derivative of the right-hand side. The right-hand side is only a function of tau r in the limits. Everything that's inside the derivative is essentially a dummy variable, right? There's tau r. It's only in the limits. So Leibniz rule says when we take the derivative of something like that, so the derivative with respect to tau r of this right-hand side is d tau r of this integral. It says bring this in as a partial derivative and then take what's being integrated over, evaluate it at the limit, and multiply by the derivative of the limit, minus what's inside evaluated at the lower limit times the derivative of the limit. So that's Leibniz rule. Leibniz rule says, for example, if I have an integral, the integral of f of x dx, but I want to take the, let's say, the t derivative, a of t, b of t, it says take the derivative inside plus the function evaluated at the upper limit times the derivative of the upper limit minus the function evaluated at the lower limit times the derivative of the lower limit. So that means we're taking the derivative with respect to tau r. We bring it on the inside. And this first term goes to 0 because there are no tau r's in here. Okay, so in our case, this term goes to 0. What's inside evaluated at the upper limit is tau r gamma dot r. Okay, that's the wall, is the upper limit. Times the derivative of the upper limit, d tau r is 1. So this term stays. This term says take the quantity evaluated at the lower limit, the stress at the center times the shear rate at the center, which is 0, times the derivative of 0 with respect. So that's 0 also. So this one also goes out. So it's this second term that shows up. So the derivative with respect to tau r of the right-hand side is equal to the integrand evaluated at the wall times the d by d tau r of the upper limit, which just turns into 1. Pretty neat. Pretty neat. Now we're almost there. We've got 30 seconds. Okay, we put the two sides together. We have 1/4 gamma dot apparent 3 tau r squared plus tau r cubed d gamma dot apparent d tau r equals tau r gamma dot r, which is the thing we've been trying to calculate. Gamma dot r is the thing we've been trying to calculate. If I now divide through by tau r, that becomes 2, that becomes 1, I get gamma dot r equals 1/4. Three gamma dot apparent tau r plus tau r squared d gamma dot apparent d tau r. Now there's some additional prettying up that we usually do. Let's see if I've got this right. It looks like I have one more tau r than in my notes. Why do I have one more tau r than in my notes? This isn't squared, is it? Oh, it is. Okay, back. You see a typo right here. Tau r squared? No tau r squared. Okay, I made a mistake right there. So that is squared. That affects my other business. This one is squared. Carry it through. Which one is that? This one. There we go. So now we're cooking. This one goes out. That one's just a tau r. If I factor out a gamma dot apparent, I get 3 plus, and then this is tau r over gamma dot apparent, d gamma dot apparent d tau r. And we can write that gamma dot r equals gamma dot apparent over 4, 3 plus. We can put this as d natural log tau r and this one as d natural log gamma dot a. d natural log gamma dot a, d natural log tau r, because d natural log tau r is equal to d tau r over tau r. And d natural log gamma dot a is d gamma dot a over gamma dot a. So this is my final expression. So what we got was an expression for the shear rate at the wall. It's a function of these same two variables, delta PR over 2L and 4Q over pi r cubed, the two that appear in the Newtonian case. I'm going to talk next time about how to take this expression and use it in the homework for calculating gamma dot r. Now that we have gamma dot r as a function of pressure drop and flow rate, you can calculate viscosity for any material as delta PR over 2L, the shear stress at the wall, divided by this expression. And we didn't have to assume any constitutive equation at all. So I'll show you how to use that, and I apologize for going over a little bit at the end here. I'll show you how to use that on Monday, and we'll continue on. I think next Monday or Wednesday, one of the two, we're going to do teaching evaluations as well.